So with that, let me start the talk today on engineers' view of startups. Remember, I might have to go a little bit faster because I didn't anticipate Steve taking half my time. But what I'll start by telling you a little bit about, this is not a technical talk, first of all, but it's really to tell you a little bit of the experiences I had and in Xterra Communications. What is the opportunity that we took advantage at Xterra? And then share with you some of the lessons that I learned the hard way. And what I mean by that are lessons that I wish others had told me about, and maybe I would have avoided some of those mistakes. And then finally really come back around to what this talk is really about, which is to encourage faculty and students to participate in startups. So for a technology to turn into a company, there are two prerequisites. First, there has to be a clear market need. Now that market need often can arise out of a paradigm shift that's going on. The other thing is that the technology that you have, the solution that you have, has to have clear, sustainable competitive advantages. If you have those two prerequisites, then to turn into a company, you still have to do a lot of work, and that's the execution pathway to go from R&D concepts into commercial reality. Now, by way of example, let me show you what we did at Xterra. I had a project here at the University of Michigan that we called the SATIN project, Soliton All Optical Terabit Interchanges and Networks, very long name. But what it really was about is terabit networks. We started that project here in 1992, and it was ongoing through about 1999. Around 1996, 1997, what became very clear was that there was a hockey stick going on. That is to say, it was the internet that was exploding, and it was going to overrun the bandwidth of the telecommunication system. It was going to need a lot more bandwidth than voice or data. So really the opportunity that we saw was, gosh, how do we feed the internet? And we had a very simple concept. Bandwidth should be like closet space. The more you have, the more you're going to use. So how do we do that? And like I said, this is not a technology talk, but this is just the one slide I have on a little bit of the technology. We had a technology in our group, just one nugget of the technology that are called Raman amplifiers. Again, not to get too technical, but what a Raman amplifier is, if you take a glass fiber and you put a pump beam down that fiber, the laser beam shakes the glass matrix, spits out a vibrational node that's called an optical phonon, and then provides gain to a longer wavelength signal. So the signal coming down sees gain. Now, in an optical fiber, it's usually used for long-distance communications. And when you do long-distance communications, one of the figures of merit is how low loss is it, or how little attenuation it has. As an example, if you look at an optical fiber, what's called fused silica fiber that's used in telecommunications, there is a very low loss window between about 1,300 nanometers and 1,600 nanometers. And that's what's known as the telecom band. Well, at the time that we were looking in 1996, there was an established amplifier technology that was called an erbium-doped fiber amplifier, EDFA, but it only occupied what's commonly called the C-band or conventional band. And as you can see, the C-band is a very small fraction of the overall window. There's actually quite a bit of research going on at various labs throughout the world where people were looking to potentially double that bandwidth to include the L band or the long wavelength band. But to do that, you had to have multiplexers, demultiplexers, you had to have two amplifiers in parallel, you had to have a guard band between them, so it was still somewhat complicated. The opportunity that we saw was that the Raman amplifier could actually cover the entire window of the low loss in the fiber because it was a property that was inherent to the fiber. And in particular, what Xterra did is they focused on creating an amplifier that covered the S, C, and L, the short wavelength, long wavelength, as well as the conventional wavelength band. So what were the properties of the Raman amplifier that we saw were key? One was that the amplification process itself was wavelength agnostic, which is to say I could put it at any wavelength I wanted, covering any window I wanted within the low loss window of the optical fiber. And that, of course, meant that we could provide a lot more lanes of highway, a lot more bandwidth. The other feature is a little bit harder to explain here, but in a Raman amplifier, you actually pump the transmission line, so the signal never gets as weak. What that means is that you can get a 5 times better noise performance in a Raman amplifier compared to the conventional technology of erbium-doped fiber amplifiers. And so we had bandwidth, and we had better noise performance. And to draw an analogy to electronics, in electronics you often have a transistor, you create a computer or whatnot using integrated circuits. In our case, the optical amplifier, namely the Raman amplifier, was the transistor. And we used what's called wavelength division multiplexing, basically putting lots of lanes of traffic down the fiber, many colors of light, which serves the purpose of the integrated circuits. One thing that we were very fortunate about is, just like in any kind of portable device, the key technology is the battery and how good the battery is. In the case of optical communications, or the Raman amplifier, our power supply were the laser diodes. So we were very fortunate at this time that the powers and the commercial availability of the laser diodes really became very prominent. So what the team at Xtera, we had about 210 people at Xtera at its peak, and what the team at Xtera did is they took these fundamental physics advantages of the Raman amplifiers and turned that into a system value proposition. In particular, what Xtera's product does is it provides a wide bandwidth, in particular 100 nanometers wide, which permits 240 channels, simultaneously a long reach, in particular between regenerators having a distance of about 1,500 kilometers. In comparison, the competitors had more like 32 channels over distances of 400 kilometers. So we had a 3x advantage this way and a 3 or 4x advantage the other way, i.e. an order of magnitude advantage. One of the things that I learned as I worked with this very smart team of industrial folks in our company was they actually figured out something that hadn't occurred to me, but actually, you know, if instead of having 3 amplifiers, if you have 1, then you need only 1 monitoring system. You don't have to have the multiplexers, demultiplexers. You can have a combined set of pumps. All of those things actually lead to a much lower cost amplifier. In particular, the figure of merit in telecommunications of what's called a price per DS3 mile, and whereas most competitors had $1.50 to $2.50 per DS3 mile, the Xtera solution turned out to be about 39 cents per DS3 mile, because they could get rid of all those extra parts, basically. And so bottom line is we had the opportunity where, based on the fundamental physics of Raman amplifiers, we could not only provide more functionality, but at a lower cost. And so roll forward a couple of years, what we ended up doing is develop a full end-to-end system. This is a snapshot of, if you were at a telephone company central office, this is what you would see. You would see 3 racks of equipment, somewhere an Xtera logo on it. Again, this was, we called it a new wave system. It was a pun on the book New Things, so this was our new wave at least. Again, remind you this was based on University of Michigan Raman technology, and again, because of the cost advantages, we've actually been able to set a new price point in the industry. And as an example of the acceptance of this technology, in the past year we've had about $40 million in sales. As an example, the British Broadcasting Corporation, BBC network in UK runs on Xtera system. Flag network between London and Paris runs on Xtera system. And again, they're still trying to sell a lot other there as well. There's also a very strong intellectual property position. There's about 46 patents that protect this product, more than half of which are licensed from the University of Michigan. And again, this whole concept of how the system is built really exploits the advantages of the Raman technology, both in terms of bandwidth and in noise performance. And again, lower cost as well. There's a couple of things we did, and I want to comment on these as we go through the talk. One thing is, by accident almost, insight, whatever, we started with 2 purchase orders. Now, very few companies start with purchase orders. We actually had a purchase order from Sprint and Nortel, which happened to be members of the Saturn Consortium here at University of Michigan. And you know, it was actually not a difficult sale, because as they got excited about the Raman technology, it occurred to me, you know, how about you give me a purchase order? Because if I don't deliver, it doesn't cost you anything. And if I deliver, you're way ahead of the game. And they thought the logic of that and that sounds pretty reasonable. And again, what was in it for them is if they had the technology, they would have a 6-month head start on their competitors. That was what's in it for them. The other thing, so that was actually, like I said, an accidental step that worked well. The other thing is we had to move the company from Ann Arbor to Texas in 2000 in order to rapidly grow the company. I'll comment on that in a moment. And the other thing, oh, by the way, we raised almost $200 million in venture capital. Always helps to have a little extra money in your pocket.